We did a bunch of stuff about counting. And I said one of the questions is, how likely is something? So if I have a collection of things that could happen, how likely is any one particular thing to happen? I need to start with some terminology. An experiment returns an outcome. But that outcome is unknown until the experiment is finished. In some sense, we can think of it as a random outcome. But our definition of randomness would be, need to figure out what that would mean, but I'll just say it's not prior determined. My sample space S is the set of possible outcomes of my experiment. Now, this means that we are going to have to define the things in this sample space depending on what sort of experiment we're looking at. And then an event is some subset of S. It could be all of them, but that's kind of boring. So more often we're talking about a proper subset. It is possible to have sample spaces that are countably infinite or even uncountably infinite, but I am going to deal with finite behavior. We'll leave infinite behavior to the prob and stats courses. If you're interested, please come talk to me. There are lots of different ways to discuss the way in which we look at probability there. The word discrete in this case means that the type of outcomes we are looking at are distinct events, separate from one another. Like, if I tell you to pick a card from my lovely standard deck of cards, you know how many outcomes there are, right? But there's no way I could say, tell me how tall someone is, because I can measure that to as many decimal places as you want, right? So in this case, discrete here is kind of like the antonym for continuous. I want to make the division between discrete and continuous again is something we'll deal with in the problem stats course. In the case where I am dealing with finite sets, probability is just a ratio of count. How many ways can you get the event you want out of how many possible things? But That underlined phrase means something. The hell does that mean? I'm not sure I agree with that. Here's an experiment. Roll 2 dice and add the number of spots. What are the possible outcomes of this experiment? 2 through 12. Each of those is unique, right? But how many ways can you get a 2? There's only one way to get 2. That way. How many ways can you get a 3? Okay, 1. They're unique outcomes. 3 is definitely different than 2, but there are more ways to do one than the other. So I need to make sure that that equal likelihood means that each outcome, not each event, but each outcome has the same chance of happening. So I think I made a mistake when I said the outcomes were 2 through 12. I think I want to think of those as events, not as outcomes. But if I just said, give you the possible numbers you could get when you add the spots, 2 through 12 is absolutely a good set of outcomes. They're just not equally likely. So equally likely means that each individual outcome has the same chance of occurring. If all of my outcomes are unique and distinct, different from one another, then I think I can agree with your sentence. But I need that difference. This guarantees me one piece of information about this number P of E. The following 2 sentences are always true. I'm counting things, right? The lowest possible number of things I can count is 0. And if E is a subset of my sample space, then the size of this numerator is never bigger than the size of the denominator. This fraction is never bigger than 1. Usually I write these together. Pick a card, any card. Chance you get an ace. All I have to do is count the number of aces, count the number of cards. Now, again, you can give me a decimal. You could reduce this fraction. You are welcome to give me this any way you want as a number. What is the chance that you get a club from a standard deck? Exactly. Which would then be 1 out of 4. Let me go back. My dice. I would like to know how to not make a giant mess on the floor here. Oops. We'll talk about this game in a little bit. I would like to know how to write out my outcomes in a way that I can guarantee that they're all equally likely. So let me just think about my experiment being, I'm going to roll 2 dice. And yes, I'm a geek. Because if you really want, we could roll other dice. I brought all of them. But we'll roll normal dice for now. How many possible outcomes are there? Wait a minute, that's just a counting question. You're going to roll these 2 things. How many possible things could happen? Why?
6 squared because each dies 6 possibilities.
I want to roll that die and I want to roll this die. There are 6 options here and 6 options there. Aha. Again, I'm going to make an assumption. I'm assuming that these dice don't pay attention to each other. There's no brain in this red die that's listening to what's going on in this white die. They're independent of one another. You have a question?
Yeah, you said outcomes, and then you were talking about experiments, and that's where I'm asking, like, would the 36 be an be possible outcomes, or would they be possible experiments?
The experiment is I'm rolling 2 dice. Notice the difference between this and the experiment I said before. The experiment I said before was roll 2 dice and add the spots. So I'm just rolling the dice and I'm counting how many outcomes are available. All right. List them. Write them all down. Write all 36 of these outcomes out. You could, if you wanted to, use a decision tree. I roll my first die and there are 6 outcomes. I roll my second die and each of those branches gets 6 more. I think it's probably easier in this case to lay them out as a table. Now, my dice happen to be red and white, so I can even go so far as to say which die is which so that I can tell them apart, right? Because then I can tell the difference between rolling a 1 on the red die and a 2 on the white die, as opposed to rolling a 2 versus a 1, right? And I can just keep going. Now, I've written the first number in my ordered pair to be the row, and the second one to be the column. E1, 4, 1, 5, 1, 6, 1. I'm going to leave off the parentheses at this point because it's just going to get in my way. Now, this set of outcomes is the only set of things that could happen when I roll 2 dice. 2d6. What I do with this information after that is separate. Are these outcomes equally likely? Ah, you two are sitting next to each other. You say yes, you say no. What the hell? Ah. That's this outcome, right? That's this one. Emily, you said no. Why are these outcomes not equally likely? Am I more likely to get the 2-4 or the 3-1?
Uh. 2, 4, 3, 1, those two are. Those two are equally likely.
As a matter of fact, what I said was, are these outcomes equally likely? As opposed to these events, I'm considering each one of them a singleton, right? Each one of them is unique and distinct from the others. There's no other way to get a 2 on the red die and a 4 on the white die than this one shot.
But you said the outcome, not.
I said the outcome, not the event. Why I put the terminology up there, so we could differentiate between the two, right? Now, what I can think of is now any question involving these dice. What's the chance I roll a roll whose sum is 3? How many ways can I roll a total of 3? Well, that's these two options right here, isn't it? My event is that the spots add up to 3. That's a subset of these outcomes, not an individual outcome. What's the chance I roll a total of 7? Out of 6 out of 36. There's your answer. So what I need to be able to, what's the chance I roll a roll whose total is odd? I'd have to add up all the possible ways of getting an odd result, right? So it could be a total of 3. It could be a total of 5. It could be a total of 7 or 9 or 11, right? Because my totals only go from 2 to 12. Lo and behold, there are exactly 18 of those outcomes. 18 out of 36 turns out to be half. More dice. How many options? You own a calculator. Give me a number. It's a lot of options, isn't it? More dice. Lots more options, right? My sample space can get huge fairly quickly. This, by the way, is now 6 to the 30th. I saw you type it in, Seth. Just give me the exponent. 10 to the what? Time to get on that big integer calculator on Google. 6 to the 30th is freaking huge, right? This number is insanely large. But this is a fairly fun dice game. We'll talk about it a little more in a bit. If I think about just card games, things like poker. I get 5 cards of 52. We came up with this number last week. How many options are there for a 5-card poker game? And where did that number come from? Because there are 52 cards for me to pick from. I get 5 of them, and the order in which I get them doesn't matter. So now I can discuss different hands in poker. I don't know how many of you know how to play poker. Anybody in the room not know how to play poker? Okay, a bunch of you. So it turns out in poker, once you get your 5 cards, you can then mix and match and rearrange and try and look at the options you can get. The rarer an option is, the more valuable that hand is. The most valuable hand in poker is a royal straight flush. Straight, the cards are in order: 10, jack, queen, king, ace. Flush, they're all the same suit: royal, a jack, a queen, and a king. That's the highest possible straight you can get. What's the chance you get one? All I need to know is how many ways that can happen.
Times itself 5 times.
No, because that 52 times itself 5 times would assume that I could get the same card twice. Right? 52 times 50, that's our combination number. The size of my sample space is this. This number right here. This is the size of the sample space. So my event now is a royal straight flush. And what I've shown you is an example of one. There's only 4. I can either get it in spades, clubs, diamonds, or hearts. That's it. There are a total of 4 possible royal straight flushes. So the chance of getting a royal straight flush is 4 out of 2598960. Period. End of story. Do me a favor, please. Simplify that fraction. Bottom is divisible by 4, so if I can just write this as 1 over something, that would be interesting. Or roughly 650,000, right? When I bought this deck of cards, it came with a ranking card. It assumes you don't know how to play poker. And so it tells you the strongest possible hand is at the top. And as we go down this list, those hands are worth less and less because they happen more ways. But what do you see at the end of that row right there? the chance of getting a royal flush is roughly 1 in 650,000. That's the number we came up with, isn't it? A straight flush, they don't have to be 10 Jack Queen King Ace, but it could be like 2 3 4 5 6, as long as they're all in the same suit. 4 of a kind. I get 4 jacks and then something else. Oh, wait a minute. There are only 13 possible ways to get all 4 of something. But then there are the other card, right? So if I can count the number of ways to get these things, I can then do this calculation and come up with roughly 1 in 4,000. I don't know if you're going to play poker. I don't know what game you're going to play. I don't know if you're ever going to play a game like this. But this is exactly the same sort of outcome I can run for any of this. We figured out the ways to get pairs, right? We counted the number of ways to get a pair last time on Wednesday, a week ago. Same idea. Okay. Who's ever bought a lottery ticket? What's the chance of winning the Powerball? Okay, wait a minute. How many possible Powerball tickets are there? How do you choose a Powerball ticket? You pick 5 numbers from what to what? Go to the website. Powerball has got its own website. Let's go look it up. These are the red ones, and these are the white ones. So when you fill out your lottery ticket, it asks you for which 5 white numbers you want and then which red number you want. Your Powerball is the red one, right? Okay, great. How many ways can you fill out a ticket? If I do 69 to the 5th, it means I can get the same number twice. Can you repeat a number? You're bubbling in a bubble sheet. Can you bubble in the same number twice? So I can't repeat things. Does the order in which I get the numbers matter? If I get the numbers 1, 2, 3, 4, 5, and they draw the numbers 5, 3, 2, 4, 1, do I win? Yes, I do. In this lottery. It says quite explicitly, you just have to match the numbers. You don't have to match the order. Do I use a permutation or a combination? Use a combination. So to get these 69 of 5 out of 69, I do 69C5. And what do I do when I hear the word and? Multiply. 26, choose 1. Multiply for me, give me a number. These are the total number of ways to fill out a lottery ticket for the Powerball. There are 292,201,338 possible Powerball tickets. What's your chance of winning? 1 in.
Depends on how many Powerballs you buy.
So, but it's still 1, 2, 3 in, right? Unless you're gonna go blow, I don't know, a couple hundred or a couple $1,000, you're not gonna get above maybe 10 or 20 in this, right? Seriously, I don't wanna be one of those people dragging a shopping cart buying 8,000 lottery tickets today. Tickets are $2 a piece. If you happen to have $584 billion lying around, you buy them all, you're guaranteed to win. Is that a worthwhile return on investment? But we saw people try it. When?
Over like 600 million, I believe.
If it's, it's $292 million. Sorry, $584 million to buy one of each. If the prize is over 600 million, I'll make money. The prize got as high as 1.4 billion once. I go to the bank, I say, look, I'm going to buy one every Powerball ticket. I'm guaranteed to win. If you were the bank, would you make me that loan? Why not?
If more than one person wins it, you have to split it.
So it's quite possible I could get only half of that, or only a third of it, only a quarter of it. I could be the guy who ends up with his entire group from the factory in Detroit, where they all won one lottery and they split it between them all, and basically nobody got anything. It's a very small payout at the time. By the way, the Mega Millions is the same idea, and they just recently raised the price of that ticket to $5. Makes your return on investment a very different calculation, doesn't it? Is it worth $2? Abso-freaking-lutely. I can't even buy a cup of coffee for $2. I can buy a lottery ticket and sit and daydream for an hour. I'm perfectly happy with that. But Seth, you gave me a comment about using, a 69 to the fifth here, right? And I need to think about the way in which I draw a lottery. The way in which I draw numbers or cards or whatever for any event changes. Ian, you said this to me the other day when we were talking about drawing 2 cards from the deck. Do I put the card I drew first back? So we can think about whether we draw with or without replacement. If I draw with replacement, I'd like to know the chance of getting 2 aces. So if I draw with replacement, I can say, okay, shuffle, shuffle, shuffle. I picked a card. What's the chance this card's an ace? 4 out of 52, 1 out of 13, right? Then I put this card back. Shuffle, shuffle, shuffle. I draw a card. What's the chance this card is an ace? The same thing, right? They're independent trials from the same deck. So my chance of getting 2 aces would be 1 out of 169. But how does this change if I have the drawing without replacement? Before I actually do any math, do you expect this to be a higher chance or a lower chance? See a couple people, I heard a bunch of mumbling.
Lower.
I got one higher, I got some lowers, I got, wait a minute, we should figure this out. Okay, wait a minute. I'm gonna pick 2 cards. Shuffle, 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 2 cards. Wait a minute, 1, 2. There, because this isn't the card. Here are my 2 cards. I need to know the number of ways in which both of these are aces. How many aces are in the deck? And I wanted to get 2 of them. How many ways can I do that? Why 12? But that's only if the order matters. What you've given me is 4P2. You said 4C2, but what you've given me is the number for 4P2. So really what I need to do is I need to take that number and divide by the number of options that are equivalent, right? Hearts, clubs versus clubs, hearts, those should count the same. So if I do 4C2, it should be 12 divided by 2, giving me 6 options. But what's the size of my sample space? A sample space is, I'm counting them. I'm not doing a probability. What's the sample space? How many possible pairs of cards are there? Say again?
52 times 51.
Then order matters. You're giving me a P, not a C. Think. Is that right?
Possible ways to do that.
Yeah.
I pick it up.
I either pick ace 2 or I pick 2 ace.
Yeah, two possible.
So this is 52 times 51, that's the permutation, but there are 2 options for each pair that's equivalent. So the total number of ways I can get 2 aces is 6 out of 2652. I'm sorry? I didn't divide by 2? So this is 1326. Thank you. Reduce this fraction. Make it smaller. Which is smaller than 1 in 169. Without replacement, it's less likely than with replacement.
Let's say that I did it the other way of doing 1/13 times 3/51. I got the same answer. I got 3/600.
But let's figure out why that version works. Yes. Why does that version work?
I took one out of the, 4 aces and one out of the 52 for that ace.
Aha. I thought of it as I got 2 cards and I dealt with both of them together. You're thinking of getting 1 card at a time. And the chance of your first card being an ace is 4 out of 52, 1 out of 13. Your second card, because I'm assuming I got an ace already, and I have 1 fewer card to deal with. That's exactly correct. That's going to be the same answer. So you can do this 1 card at a time, or you can do it by counting the sets of cards. I think this method is a little faster, especially when we start dealing with larger collections. 1 card at a time is a much harder thing to do when you deal with 5 or 6 or 7 cards, right? But the process works. Questions? I've now done this several times. I said, and what do I do when I hear the word and when I'm counting? I multiply. Well, what do I do when I hear the word or? What do I do when I hear the word not? We came up with formulas for those for counting, didn't we? If we know the formulas for counting, we know the formulas for probability. All we have to do is divide by the sample space. The chance of something not happening is 1, the chance of anything happening, minus the chance it happens. Pick a card. What's the chance you don't get a queen? That's really kind of hard. There are a lot of options that aren't a queen, but there are very few options that are queens, right? So I say, oh, well, there are only 4 queens. Take those out. Take those out. Let me step that problem up. Emily, I'm gonna push here, and I'm gonna say it's much harder to do this 1 card at a time than it is to do it in sets. If I want you to pick 5 cards from our shuffled deck of cards, what's the chance you get at least 1 ace? Problem is I could get 1, I could get 2, I could get 3, I could get 4, right? What can't I get? Can't get no ace. So what I could say is that this is 1 minus the chance of that. Oh, wait a minute. Wait a minute. If I never get an ace, how do I count how many ways I can get 5 cards and none of them are aces? Does the order matter? Am I allowed to repeat cards? Oh, you know, I'm picking all 5 at once. There's no replacement here, no repetition. Permutation, combination. Which one do I use? B or C? Combination. So I'm going to do a combination, and I'm going to get 5 cards. Out of, I'm not allowed to use any of the aces. Out of how many possible cards? Oh, out of all 52 card hands, 5 at a time. Grab a calculator, give me a number. But it's much easier to do it this way than it is to say, oh, I could have gotten 1 ace, or 2 aces, or 3 aces, or 4 aces. What do I do when I see the word or? We hadn't mentioned that yet. I can go up the creek, wouldn't I? We'll figure out that in a minute. What's this chance? Give me a decimal. It's much easier as a decimal. For this or for the whole thing? Yes, that's what I got. I was expecting somebody to give me the 0.66, which is this calculation. It would be 1 minus 0.66, which is 0.34. Absolutely. What do I do with that word or? What do I do when I see the word or when I'm counting? There's a counting formula using the word or. Go look, it was in your notes from Wednesday last. Might even be from Friday the week before.
Get rid of the doubles.
When I counted A or B, I counted A, I counted B, and I subtracted the overlap. Well, if I'm doing a probability, I'm going to do the probability of the first plus the probability of the second minus the probability of both. Exactly the same formula. So if I was counting it by, I could get 1 ace or 2 aces or 3 aces or 4 aces, I'd have to figure out the chance of getting 1 ace, the chance of getting 2 aces, the chance of getting 3 aces, the chance of getting 4 aces. I'd have to add all those up. They can't have any overlap. You can't get 1 ace and 2 aces at the same time. So this part would be a 0. This game is called Liar's Dice. Anybody ever played Liar's Dice? I claim I have at least 2 5s under that cup. Now we're sitting in a circle, and I look at the person to my left and I say, do you believe me or am I talking out ants? If they believe me, they get the cup. And they get to say, I claim I have either 2 6s or 3 something. You have to either raise the number of spots or the number of dice. And we keep going around the circle until somebody says, I don't believe you. And then we uncover the dice. And if they're right, they win a point. And if I'm right, I win a point. This version of the game plays with everyone's dice. Instead of me passing this set of dice, everybody gets their own cup with their own set of dice. And my bet is on all the dice. Oh, and in that version of the game, ones are wild. So this was actually 3 5s. And that's why the game is called Perudo or Dudo, I doubt, in Spanish. In any case, the game is based on the idea of expected value, which is calculated using our rules from probability. I will be more than glad to teach you all about this game. Take Prob and Stats. In any case, I will see you all on Friday.